I start by thanking the organizers for putting this workshop. Very nice, and it's an honor to be here. So I'd like to tell you about a machine learning perspective on the many-body problem in classical and quantum physics. So let me first acknowledge my machine learning friends, my quantum physics machine learning friends. So Roger Melko at the University of Waterloo, Giacomo Torlai, Giuseppe Carleo, who is here from ETH, Matthias Troyer, and Guglielmo Mazzola. So I'm going to introduce the problem very informally, using the complexity or the complications that we see or that we experience when we try to study many-body problems in quantum physics. Okay, so the many-body problem in quantum physics. So the first postulate of quantum mechanics says that everything we can possibly know about a wave function or a quantum system comes out of the wave function of the system, which is this vector here, which has typically an exponentially large amount of information in the size of the system, let's say n, so it's exponential, and so it's just intrinsically a big data problem if you want, and is such that even with today's best supercomputers, you can solve the wave equation or the Schrodinger equation for psi exactly for up to, let's say, 45 particles, which is pretty small. And that's using like big supercomputers. So big problem, and it's so bad that storing the state of a 273 spin system requires a computer with more bits than there are atoms in the universe. So that's what we like to say. Like I think any condensed matter would argue that, and condensed matter physicists, and yet very important problems in chemistry and condensed matter and quantum computing are way larger than 273. Okay, so what do? There's quantum computing that we're still trying to figure out, so it may help in the future, but what can we do before we have quantum computers, right? So there's still hope for classical algorithms because nature is sometimes compassionate, even though I don't think nature cares about us. But many-body system can be typically characterized by an amount of information smaller than the maximum capacity, right? Like this exponentially amount of information, and that's what we exploit when we do, for instance, and when we study quantum many-body systems using quantum Monte Carlo simulations or tensor networks. We exploit the fact that we can characterize correlation functions and observables using a smaller amount of information. Okay, so in QMC what we do is we sample the state space stochastically, and we're still able to get pretty accurate correlation functions and so on, even though the system in principle is described by an exponentially huge amount of information. And the same is true for tensor network methods. We use them, we exploit that they are low typically some states in nature are low entangled, and so here is like a diagram of Hilbert space, and here is QMC, which solves some problems. There's tensor networks, which solves some other states in nature. Some of them we can solve, and then generic random states. So we use techniques, and in spite of this curse of dimensionality, and the same is true for the machine learning community. Okay, machine learning community deals with equally high dimensional problems, even bigger than those that we care about, right? Like I heard last week, some GANs using like really high resolution images, like it's incredible, like, and they battled this curse of dimensionality successfully, right? Like, and with impressive results in a wide spectrum of scientific and technologically relevant areas of research. And they use neural networks typically. And so quantum physics is not the exception, and there are a big bunch of new work coming out, like with classification of phases, inspired machine learning inspired answers for quantum many-body systems, quantum state preparation, accelerating Monte Carlo simulations, renormalization group, quantum state tomography, and more, and they keep coming every week. So that's exciting for quantum physics, and so the list is obviously incomplete, but let me go on. So in this talk, I will discuss several applications of machine learning ideas to problems in many-body physics. In particular, I'm going to tell you about supervised learning approach to classical phase transitions. I wrote quantum, but I don't have any quantum for this talk. I'm going to interpret the wave function as a generative model of the reality that we see, and using that idea, I'm going to write down the ground state of the Kitaev storic code using convolutional neural networks, and then using those ideas, I'm going to focus on a slightly less toy problem, and I'm going to show a data-intensive problem in quantum mechanics, which is that of quantum state tomography, using neural networks, in particular RBMs. Okay, so that's kind of like what I want to do, or what I want to tell you. So the first idea is supervised learning perspective of phases of matter, right? So it's very simple. It's a toy exercise, but still fun. So I'm going to use the Ising model, which I think most of you know. Like, either you come from machine learning or from physics. I think most people have seen it, but let me introduce it. So this model is characterized by this energy function E, and these variables sigma I, sigma j are just plus or minus 1, and those variables are located at on a square grid. There are those variables here. What we know about it is that at low temperature, the system magnetizes either up or down, just to minimize the energy E. As you warm the system up, it starts like getting a lot of like thermal fluctuations, and then there's a phase transition in between the low temperature phase where you have magnetization and the high temperature phase where the spins basically are completely random. Okay, so that's the Ising model, or the very rough description of it. And what we know about it is that there's a phase transition between the low temperature and the high temperature regime, and the phase transition is characterized by an order parameter called magnetization, which is basically the average or the expectation value of the average over the spins in the lattice. And we know that at low temperature the magnetization is finite, and at high temperature it goes to 0. The critical point that was predicted by Lars Onsager in the 40s. So it's a pretty well understood problem, but for the sake of understanding machine learning techniques, that's what we started with, okay? So what do I mean by machine learning phases of matter? The inspiration came from this MNIST classification problem. So the way I understood MNIST is that, for instance, a 5, like the one here, can be understood as a perfect 5 that the computer can understand, plus some fluctuations due to the way humans write. Okay, so that's how you get like how I imagine like getting like a 5, like a 105. And then the machine learning community, I guess most of you have done this. Like this, like they developed supervised learning algorithms that allow you to, given an image 5, you get outcome from the neural net a perfect 5, a 5 that the computer can understand. And so that's what I thought, right? Like, so in physics, we understand typically phases starting from a mean field perspective. So for a ferromagnet, it's basically all spins up or down, and then plus some fluctuations, which are those fluctuations induced by a thermal bath. Okay, and so the idea that I had is, okay, I need to understand how neural networks work, so I'm going to use this system that I understand. And so what I said, okay, I'm going to get a big bunch of measurements in the ferromagnetic phase, and another big bunch of measurements in the high temperature phase, and I'm going to use classification, right, like supervised learning. So I was like, okay, let me try to understand how this works. And then what I did was I just sampled using like this distribution P, which is basically the Boltzmann weight of the icing model, and a low temperature and a high temperature. And I got a big bunch of samples out of it, 20K samples below TC and 20K above TC. And then I prepared this like a low-dimensional visualization of the data, where you can see already everything, right? Like you see that at low temperature, which is this blue blobs, this is where like the magnetization is pretty high, right? So and you can already see, okay, one of them is spins up, and the other one is spins down. And then as you warm it up, you see the color like red for warm. Then you get only one blob where like you get only the high temperature phase, and in between there's this this transition, right? Like, so I did that. Like I did. Okay, I'm going to do supervised learning, and I have only two outcomes, right? Like because I only have two phases, and so that's this plot here. As a function, so the blue curve is what I call the low temperature neuron, and the red one is the high temperature one. And the blue activates at low temperature, and the red, which is the hot neuron, it activates at high temperature. And then the curious thing that we saw is that there's a crossing point in between around TC, right? Like what we observe is, yeah, so at TC, basically the neural net doesn't know, is this coming from a high temperature or low temperature? On average, it doesn't know, right? Like that's where we said, okay, so that should be the critical temperature, and sure enough, it coincides with the critical temperature of the model. Okay, and even more, like in figure B, you can get a collapse. So this is an idea from the renormalization group. You're able even to get critical exponents out of this type of calculation. So we were able to get nu, which is the correlation length critical exponent, pretty accurately out of the calculation. So that's for A and B, and this is perhaps the most interesting result. As initially we trained the model on the square lattice, like the Ising model on the square lattice, and then we took the triangular one, and then we get all those samples out of the triangular model, and then I used the trained neural network and to process these images that I got out of the triangular lattice, and then I was able to compute the TC of the triangular lattice out of the trained model that I got from the square. So that was pretty cool, but a little bit surprising. We said, why is that? And the conclusion is that basically it's written here. So this we wrote down an analytical model, and we understood what the neural network learns. It learns the order parameter, okay? And it basically, relies on the magnetization of the system to perform this classification. And then we investigated the arguments of the hidden layer, W times X plus B, and we plotted that as a function of the magnetization of the configuration. And so in figure A, so that's my analytical understanding. So if you want, the model I trained with my brain, and then in B is the untrained model, and in C is when you do it numerically. Then what you see is that the neurons, what you get is functions of the magnetization. So it means that the neural network uses the magnetization, or it relies on the magnetization to perform this discrimination problem. Same as Onsager did when or even before that. So that's the conclusion. And if you modify this and you change it to the antiferromagnetic Ising model, then what you get is the staggered magnetization. And in general, what we checked is that it relies on any local order parameter that you can define. So that was kind of an interesting conclusion. And the other experiment that we run is that even if you train the model in 2D, you can get the critical temperature in 3D, for instance, because for the same model, basically they share the same order parameter, and you can still make sense out of these transitions, and you get different critical exponents in 3D and so on. So that's the conclusion of the first part. And this is for phases, like what I said, is for phases which have an order parameter, right? Like, and you may not even be surprised. One, this is very trivial. I can't even tell from seeing, like, from having a look at the images that's up there here. It's basically order, we know, and this one looks disordered, so why do you even need a neural network, right? So it's a very toy problem, but then we thought, can we deal with phases which do not have an order parameter? So we wanted to understand that problem, and so basically what I have in mind is topological phases of matter, examples of which fractional quantum Hall effect, quantum spin liquids, Ising gauge theories, lots of interesting systems. Yeah.
So in order to get this result, you have to do simulations, right? And then you can classify it.
Yeah, that's right. No. We did simulations. In principle, like to mimic experiments too. Yeah. So, so then we focused on phases of matter. So there are topological ones that I just mentioned. They defy Landau symmetry breaking classification and so on. So they're richer, and like the other example I have is Coulomb phases, which are like kind of like classical or highly correlated spin liquids. They're described by electrodynamics, and like one example is common water ice and spin ice materials. So I'm going to focus on the Wegener's Ising gauge theory, which is this simple Hamiltonian here. H is described by spins that live on the bonds of the square lattice, and the interaction is given by products over the plaquettes P that I have here, and basically the energy is just this product over the four of them, and it's been studied like since the 70s. The phase diagram is known. It's at zero temperature, we have a ground state that is classical, but is disordered, so there's no order parameter, and the phase is topologically ordered. And as soon as you warm the system even a little bit, you destroy the phase and you go into the high temperature phase. And some people call the toric code the mother of topological quantum computing. I call this the grandmother because it's like half of the toric code. Okay, so I really like this system, and basically, so what we wanted to do was, can we classify configurations of this system and tell the difference between t equals 0 and infinity? And the nice thing is both the ground state and the infinite temperature state, they both have exponentially decaying spin-spin correlations. So then it becomes trickier for the classification problem, as you will see now. So here I have two configurations for the system. So one is ground state and one is high temperature state. Would you like to guess which is which? Like for fun. Yes, but you know a lot of machine learning, so. No, that's right. Like, okay, so good. I don't know how you did it, but like, so if you try like a feed-forward neural network, like a fully connected one, like the one that I used for the Ising model, I just couldn't make it work. It's very difficult to train. And you always get to 50% accuracy, which is as good as guessing, right? Like as I may have tried in the past. So so the question was what to do, right? Like how do we fix this? And so the solution came. Okay, I just started playing. Okay, with different architectures and so on. And this is the one I came up with, like for the first successful attempt, and is using a convolutional neural network with small filters that I slide around the configuration. And then if I train this I do supervised learning the same way I did for the Ising model, then I get 99% accuracy. It's easy to train, and it has all sort of nice properties. And the picture that we draw for what this convolutional neural network is doing in this case is that it uses the detection of satisfied local constraints. And by that I mean these products over the plaquettes. Right, like so we call it satisfied when the product over the four spins is 1, because we have a minus in front. So, and that's what we figured out the neural network is doing. It's just checking the parity of those products. And then that's basically the conclusion. And then based upon that idea, we just really literally wrote down the filters, right? Like analytically for that problem, which coincide with this, basically this expression here. And then if you use that analytically trained, it's not really trained, I just write down the weights and so on with 16 filters and 2x2 patches. And I use perceptrons because I don't have to train. As the activation functions, then you get 100% accuracy on the test set. So that was interesting, and we were happy. And then here it comes like a byproduct of doing that, and it's the fact that if you take the expression for the call neuron in this case, that coincides with the ground state of a quantum many-body system. So that's what we figured out. If we take, if you augment this Hamiltonian, which is this part we had, that's the Wegner's Ising gauge theory, and then you augment it with this quantum fluctuations term, which is defined over the vertices of the square lattice, then that has been analytically solved in the past. But what we figure out is that call neuron that we used in the classification toy problem is the ground state of that Hamiltonian. So that was nice and interesting, and it made sense. And so basically, as far as I know, this was like the first time that we used, or as far as I know, it's the first time that someone used convolutional neural networks to write down ground states of many-body systems. So it's pretty cool. You just take the square root of the neural network, and then you have that. So, but this was extended and improved. So Don Ling then, he wrote a paper where they did analytically the same and more by using restricted Boltzmann machines. And Jing Chen Song and Haidong Shi and Lei Wang, they did, again, solving this problem analytically with RBMs and so on. RBMs were introduced by Giuseppe, by the way, like as an answer for many-body systems, and so all this is just to tell you a message that I think is very important. Is that neural network with a small number of parameters are able to write down analytically the ground state of the system, at least in this very simple case. They seem to be very good tools for compressing quantum many-body states in analogy to tensor networks. But they have no limitations in the dimensionality. So tensor networks are very successful, especially in 1D. They're harder to apply in 2D and in 3D. Most importantly, we can devise numerical procedures to study systems for where we don't have analytical solutions like this, okay? And this has all sorts of potential applications in materials physics, quantum chemistry, and quantum state tomography. So there's a whole lot of new interesting applications. Yep.
Do the filters you get by training look similar to the analytical filters?
Yes.
Yeah. Is it stable if you retrain from a different filter?
That's right. I try, and yes. Mm-hmm. So let me give you one example out of this list. So among the potential applications, I will tell you the one about quantum state tomography. So this is more recent. So what's quantum state tomography? The problem is, can we reconstruct the quantum state of a physical system from a limited set of experimentally accessible measurements? Okay, and this is a very important question because these measurements are available in experiments and, for instance, in cold atoms, trapped ions, and even quantum devices such as D-Wave, which for which you can get these snapshots or these measurements. And this is important because quantum state tomography is kind of like the diagnostic tool when you have implementation of these technologies, right? Like or algorithms, or so we think it's a pretty interesting application and is a data-driven application. So I think machine learning is kind of like the right, or one of the right tools that we could use for this type of problems. So the problem is, again, can we reconstruct the quantum state of a physical system out of a set of measurements? And there are some requirements for quantum state tomography for large systems to work. So for small systems, you can use traditional methods, and they require exponential resources, but everything is very well defined and so on. But for large systems, you need an efficient representation of the quantum state. And in there, we either have tensor networks like matrix product states, MPS. Neural networks is one more. So, and that's what we want to do, right? Like, so our efficient representation, I wouldn't like to use the word efficient, but like a simple way to represent the state, or not even simple, but kind of like a reasonable way of representing the state, as we've seen, is neural networks. And then we need a set of projective measurements in different bases that I represent by sigma b, whose measurement probability is given by the square of the wave function, and this is basically Born's rule, written in different bases. And we need then a learning procedure that makes use of this data to learn the state. So it's an inherently big data problem, and what we did is we used unsupervised learning and maximum likelihood estimation. And our neural network is the RBM, because it's suitable for systems in basically any dimension. It has compact representation of the states, and there's all sort of available tools like for the evaluation of the quality of the results, like log likelihood, overfit, like we can check for overfitting and so on. And RBMs can also encode highly entangled states. So in this paper by Don Lingden and collaborators, they've shown that they can carry a lot of quantum entanglement. So that's our choice. And the most important assumption that we have is that the state is pure. So basically, that's our weakest point, or strongest assumption, because in general the states are mixed. But there are still some interesting properties. So they're easy to handle numerically. I mean, RBMs, they have been extended to a wave function by in this paper by Giuseppe Carleo, who used it as a variational ansatz for quantum states. So they can meaningfully represent quantum states. There are all sorts of results, exact representation of topological states, and they've been used for all sorts of different things. So we like them in physics, even though I understand in machine learning they're not so popular anymore. But other choices are possible, right? Like as I've shown CNNs work for the toric code, but in this case we use RBMs extended to the complex domain. Yeah.
One of the reasons why RBM is not it's just difficult to train large RBM, and then also you can have a good partition function and so on.
Yeah, because you can prove all sorts of things with them. You can show the entanglement properties. You can sample them even when they're complex. So they're easy to handle, at least from our point of view. Yeah. And we don't typically compute the partition function. We don't require it. So they work pretty well for our purposes. Yeah. So what we do is, the goal is to find basically the parameters of this extended complex valued RBM, and we do that basically by defining KL divergence on this different basis, or in these different measurements that we took, or that we hope one day we would get out of the experiments, and then we minimize this divergence, which we then average over the different various experimental measurements or synthetically generated data sets. We use stochastic gradient descent as well as natural gradient descent in some cases. And so here's one example. So here we took this state. It's very popular in quantum optics. It's just a superposition. So it's this one here. Superposition of 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, 1, 1, and so on. And then we took measurements on the Z basis only for this. And then what we did was, let's reconstruct the wave function. And then what we did here is, in this case, we can compute the overlap of the reconstructed wave function with the exact one, only for this particular case. And what we see is that as we grow the size of the data sets, we get an overlap that grows with this parameter ns, the number of samples that we use, and then it converges to 1 pretty quickly. So it means we're learning the state pretty well. And so we were happy, but we wanted more, or the referee wanted more. And they like to, typically in general, the wave function is not real, and the one we had there was real, so we introduced these complex phases, which makes the problem a little bit more complicated. And then we had measurements in different basis sets. In this case, we have this basis, so XX, ZZZ, ZXX, ZZZ, X, Y, XZ, and so on. So we had all those, and then we performed this this technique, this like extended KL divergence minimization, and then we got that we were able to reproduce the phases pretty well. So the exact ones are here. So the colors mean nothing. It's just that the amplitudes are this. If you want this, the size of this figures. And then the reconstructed ones are in here, like from the RBM. So we were able to show that it works pretty well even in that case. We took also many body systems, like the one transverse field Ising model in 1D for relatively significantly large systems. And here are correlation functions obtained from quantum Monte Carlo, and here are correlation functions for the restricted Boltzmann machine. So they match relatively well with some noise, but that's fine. And we were also able to measure, like to reconstruct the wave function for the two-dimensional transverse field Ising model. And here are reconstructions of the observables as a function of the transverse field H. And even if we just use the measurements on the sigma Z basis, we're able to reconstruct observables which are off diagonal pretty accurately, right? Like those here in blue are reconstructed out of the RBM. So it means that the RBM has some sort of like generalization when you try to take measurements which the wave function has never seen, right? That was interesting, and the same is true in, like, for the 2D XXZ Hamiltonian. And finally, the most interesting result is when you want to compute entanglement, because for experiments, this is a very challenging quantity to compute or to get experimentally. But what we're proposing is that we can do quantum state tomography, and then once you have this wave function, the RBM or the complex RBM, you can then compute entanglement. And what we've shown here is that when we try to do that, we're pretty successful, right? Like, black is results from exact diagonalization, and the dots and squares and so on are results from obtained from the restricted Boltzmann machine. So for experiments, this is like a way to get this entanglement measurements. And the meaning for the RBMs, or what I would like to say, is that it shows that it really learned to generalize very well, because when you're doing this type of entanglement measurements, you really need values of the wave function or the RBM that are pretty far from the training set, typically, especially when you have pretty large systems. where like the size of the training set is really, really small compared to the size of the Hilbert space. Okay, so let me finish. So we encode and discriminate phases and phase transitions, both conventional and topological, using neural network technology. And we have a relatively solid understanding of what the neural nets do in those cases through very controlled analytical calculations. And we have performed quantum state tomography based on neural networks and RBMs. And we think this is very promising, at least like for quantum state tomography. And let me finish by saying that we have some research scientist positions and postdoctoral fellows at the Vector Institute, as well as PhD studentships and so on. So with that, I would like to thank you.
So we have time for maybe a couple questions.
What do you mean by size? By like the system size?
Yes.
So we did that more or less carefully. Also, the question is, when you change the system size, what happens, right? Like that there's a dependency of the critical temperature. So what we did was, what we've shown is that as we grow the size of the system, the critical temperature approaches, and it goes closer and closer to the theoretical result for the infinite system. That's what we've checked. I just don't have a plot here. And then, but yeah, so typically, as you grow the system size, you approach the analytical result when there is one. Mm-hmm. Yeah.
So this might be an off-the-ball question. Lots of deep learning has been successful because we've got useful modules that we can stick together and differentiate. So, convolutional modules are successful, LSTM cells, and people do things like look around for fast algorithms that do something useful and put it in their neural nets. So people have got fast Fourier transforms and insert them into their neural nets. So I'm wondering whether there's any technology transfer we can do here where is there an existing algorithm that would normally be used to analyze these systems that we could pull out as just some function that we could differentiate and use as part of a function representation and learn something from all the analysis that's already been done in these systems?
Yes, so I have several ideas about that. So one of them was already exploited by our friend Miles Studenmeyer, is this supervised learning using tensor networks. So tensor networks are this representation of a function or a wave function, and they've been pretty successful in physics. And so what Miles did was use those to perform supervised learning. And then this was extended to unsupervised learning and so on. And I think there's room for this type of methodologies to expand to machine learning. It's just that I don't see many people doing it. It needs more like people playing with it, as far as I know. You pick.
Fantastic work, first of all.
Thank you.
Can you expand more? So you just mentioned tensor networks. Can you expand more about its efficiency as a representation, both conceptually and numerically? Because you mentioned in the talk that the efficiency was higher dimensions, right? Because you have to decompose a matrix to get to the base. So is the problem just that, or can you give more flavor?
So they're pretty efficient, even like theoretically efficient when you have low entanglement. It means that the entanglement entropy of the system that you want to study is finite. It's basically a constant for 1D systems. And in that case, then yes, you can. But for instance, if you take a system to its critical point, then the entanglement it grows significantly, and then the representation is no longer efficient. So it really depends on the system that you're interested in, and so you have to be careful, like where you apply it and like. Mm-hmm.
Is your feeling just right now you're leaning towards CNN and RTM to tackle that from your point?
That's one thing I would like to work on, right? Like pursue this line of ideas, like using. Mm-hmm.
Let's thank Juan again.
Thank you. Thank you.